Professor Sample for this minute to talk to your class about the MDP program. I have some flyers. I'll leave a couple more up here if you're interested. You have a couple of current and former MDP students in your class. If you have any questions, they might be able to help you. If you haven't heard of us, multidisciplinary design is 2-semester experiential learning opportunities where you do real-world work, but you earn credit. And so we have 32 projects this year. 23 of them are sponsored by companies, a couple by Stryker and Keurig specifically, that are looking for students with experience in embedded systems, so and embedded controls. So we would love to see you check us out. You can check out our projects. We have some info sessions. There's informations about our sessions here, and a project fair at the end of September where you can meet the companies and the faculty researchers that are putting these projects forth. These are the types of activities that build your resume, that help you on career fair day. I am a former Michigan engineer, and I'm a former project sponsor at Johnson Controls in my former life, and I can tell you that these are the kinds of activities that people who you want to work for want to see, and they want to know that you can do. And so you have to also spend close contact with folks like Professor Sample and other of our faculty mentors. So those teams, the industry teams, have 5 to 7 students, and they spend 2 hours a week in a small classroom with a dedicated faculty mentor. So there's lots of exciting things that you get out of this experience. So any quick questions? Otherwise, I want to let you get back to class. Okay, great. Thanks. Well, I hope you'll check us out. If you have any questions, just find us online, like everywhere.
I will say that, if you're out there trying to get a job interview, right, that's hard. But this is easy. You're going to basically spend captive time, an hour a week for 30 weeks with somebody from industry, in a relationship that. And when I did a MDP, or I mentored one 2 years ago, and that everybody ended up getting internships at the company, which is not guaranteed. But just think about that. You're trying to make connections with somebody who's going to employ you. This is a mechanism to do that.
Awesome. Thank you.
I'm trying to use my iPad today. Let's see how it works. One small piece of news that Arjun is starting as an IA with us, kind of started late, which is great to have extra resources. So this means he'll be taking over some of the lab sections. There'll still be 2 people, but James over here, who's our new Matt Smith, that frees him up to work on more administrative tasks. So you'll see some new faces in there. Yeah. Any questions before we get started? Let's see if we can make it work today. Fancy. Okay. So today we're going to talk about new stuff. So let's do some announcements. Homeworks 2 is due today. Homework 3 has been posted and is due in a week. Office hours are on Thursdays, 3 to 4 in my office. At least those are like lecture office hours. There's open hours for lab, and you can ask the open hour lab people homework questions if you would like. Post labs and in labs are due the night before the next week's lab section. So basically you have a week to do those tasks. Lab 3 is, you're going to start that this week, and pre-labs are due before lab sections start. Any questions about labs or due dates? Very quiet group. All right. I did want to keep doing a component of a day. So last time we talked about batteries, and remember, batteries, there's different chemistries. The problem with batteries is there's not a constant output voltage. They'll say on them 1.5 volts or 3.2 volts or 3.4 volts, whatever, but they're not constant. Remember, they always have this discharge curve. And so if you're going to use those with any of your electronics, you're going to need to use a voltage regulator. And so these are all examples. Sometimes voltage regulators are very simple, like just 3 pins. Some of them are more complicated. The details aren't really that important of how they work. I just want you to know that if you're going to have a battery that's powering some of STM32 or some electronic device, you're going to need something in between. That's a voltage regulator. And the job of the voltage regulator is to control the output voltage. So no matter what the input voltage is, it's going to control the output voltage to some known thing. So your STM32s are working at 3.3 volts. So either they're fixed or sometimes they're adjustable, and you would set it to 3.3 volts, and it's going to maintain that you're going to try to maintain it no matter what the load is. So even if you draw lots of current, you're not going to have voltage drop like you would with the resistor. Here, you're going to try and keep a constant voltage. And things that you can think about, if you're going to select one or talk to one of the IAs about it, how much power is your device going to hold? There's a limitation here, or because your device consumes, you have to have one that's rated for that. And then what are your input voltage range and output voltage range that you need from these things? So just to keep in mind, these things exist and you'll need them. Any questions? You guys gotta ask questions or else I'll just keep going forward. Yes.
Wait, so is there like another power source that like provides to this to stable? Like how does that work?
Like how does it figure out how does it choose a stable voltage? Okay. So you would say you connect it with a battery, so your battery would be only a device. Internal to, if you spend more time in EE, they'll talk about something called a band gap, which is a silicon method to make a known voltage reference. So this give you like 1.8 volts or 1.2 volts. It'll be known, like it'll always be this. And then with some resistors and some op amps and other things, then they can create any voltage on the output you want. So internally, this device will figure out how to keep it at some set voltage. Did that answer your question? Yeah. Good questions. Okay. Today we're going to talk about memory mapped I/O. So this is new content that you probably never saw in 370 or 270. We're going to talk, part of that is that you're going to have to talk about bus structure. So how does data get pushed around a chip? And then we'll talk about the specific bus structure that we'll be using in this class called the Advanced Peripheral Bus. Okay, so remember this architecture diagram. I just kind of explained what memory, or the high level here. Today is about, you guys learned about the core, but a lot of this is about how we're going to push data around these different peripherals. So, kind of refreshing to bring it back all together. We have, oops, no, too complicated. Okay, so we have, this is our memory hierarchy or memory map, right? So we have, this is what ARM has laid out as the spaces pre-allocated for vendors to use to implement certain amounts of memory. So you have code, SRAM, you have memory locations for peripherals, for system, for external devices. And these pieces of memory are actually distributed throughout your system. So some of it is, code is usually put into flash. You have your data is usually put into SRAM. Your peripherals aren't in memory. Your peripherals are addressable locations that are in different subsections. So here's the peripherals for the Advanced Peripheral Bus or the Advanced High Performance Bus. And then you have those external regions, like those other regions, like external memory, external RAM. It might not be completely accurate to say that they're on this bus. They actually go through the GPIO peripherals, but they are essentially connected to those buses. So when you're doing your loads and stores, you're not necessarily just talking to memory. You might be talking to all these different locations around the chip. We're going to try and figure out what's the mechanism is which, when you say load to a particular address, how do I know how does the data get to the peripheral versus SRAM versus code? Any questions so far? You guys can ask questions. I'm not that good a teacher. Okay. So imagine, let's take an example. We have a peripheral, and you guys have been in lab, been pushing up, GPIO pins up and down, lighting LEDs. And so here's an example of, for this particular space, there's addresses that are located with GPIO A. Let's look at one memory location, a word's worth of memory location in GPIO A's peripheral. And now we can say that is represented here as a binary number, and here's some indices for that memory location, okay? So you have ones and zeros in memory. What is one possible way to physically instantiate that? What's the memory holding mechanism? What's one way to do that? I know somebody knows. You can just take a guess. Yes. D flip-flop, bravest person here. That's fantastic. Okay. So yeah, here we have D flip-flops, right? They're just state holding devices. Okay. So here, you could use SRAM. If you're in the SRAM section, you'd have a different structure. You'd have 6 transistors to make SRAM. If you were in flash, you'd have a different structure. But here in a peripheral, a good mechanism to hold that state is a D flip-flop. And as we were thinking about getting you guys set up for these concepts, we talked about problem 2. I know there are some questions here. Problem 2 is really just a review of, or homework 2, problem 1.2, is really just a review of 270 with combinational logic. That's all you have to do is put down combinational logic. But you can already see here, you'd have some registers, and then you want to control something over here, right? And what we're going to do is you can go write a word, or sorry, 4 bits into this thing, and it will control something over there. Okay? And that is no different than this picture here. It's just we're saying the cues here could go to something else. The cues could go to your GPIO pins. So just by loading or storing words into this peripheral, putting words in here, ones and zeros, now you get to control something on the outside. Okay, so that's the mechanism as which we're going to use to implement memory mapped I/O. So, I guess the basic idea of memory mapped I/O, maybe I did this a little bit backwards. I'll give you the counter example first. So port mapped I/O, this is what like Intel AMD processors would use, where you'd have instructions that are tied to a particular port. Right? So for these application class processors, or at least those processors, right, you might have instructions specifically for putting things into memory, or particularly put things in on the video, right? So this is like the north and south bus. Those are instructions coupled to that task. As opposed to memory mapped I/O, it's simpler, at least simpler from an architecture's point of view. Each device, each register, each memory address represents a place in which you can store data, and it's independent. You can just use loads and stores. You don't have to have a special command for this. So it has lower performance than port mapped I/O, but it's simpler to implement. So that's the advantage. And on these small little microcontrollers, that's an advantage. You don't want to have lots and lots of instructions. So an example of that is here. Again, just you have your core. You can store it into some memory address. You're going to take a bit off, and that's going to control something else. And we'll talk about GPIOs today, but later on it'll be timers and ADCs, or analog digital converters, and other things. So why don't you take 60 seconds, talk to your neighbor, see if you both agree on what memory mapped I/O is, and then we'll talk about it some more.
It's just interfacing with the outside world, but using
I don't really understand what's the difference between them and memory access to.
Isn't it due tomorrow? What? It's due tomorrow. Yeah. It doesn't look that bad.
Yeah, but you use the same load and store instructions rather than having special instructions.
No, the whole thing.
Yeah.
Open lab tomorrow. Okay, good.
Like if you're
Well, I can go at.
All right, so you've talked to each other. Ooh, wow.
yeah. That's why I have this weird script thing.
Okay.
What questions arose? You tried to explain it to somebody, maybe your explanation fell short or it raised other questions. What questions do you have? Yeah.
Our main thing we were talking about is how is this different than what we did in the lab, like when we were writing registers to turn on and off LEDs.
It's not. We taught you the same thing in lab. We're just teaching it from different angles at different times. What other questions? Yeah.
I was a little confused on like what exactly is the difference between that and the port mapped I/O? Like how, like what is the port as opposed to the memory, you know?
Yeah, so you could have, it's been a long time since I looked at computer architecture, so my apologies, but you can imagine that if you are an Intel chip and you have I think it's the North Bridge, which is the video port, and so you can have specialized commands that do more when you're trying to push information to the video card. That's different than just saying, I'm generally going to do loads and stores. So it might take you 5 stores to do the same thing one instruction that's port mapped could do.
But it's still going to a memory location. It's just a memory location on a port instead.
The architecture doesn't even think about it as a memory location. It's more of a command to a submodule to go do a task. Good question. Any other questions? All All right, well, you have more questions. We're going to go through more. But generally, if you can just get the idea that doing loads and stores isn't just some abstract memory, it's actually specific memory at a specific location that does a task, you're going to do fine. That's the big idea. Okay, so let's look at a slightly different example. Here we have an 1 gig SD card. Maybe 1 gig is too large. Oh no, 1 gig's fine. I said the example right. You're going to use loads and stores to put data into there, right? So this is off chip, okay? And you can't load directly into that. You're going to go into some memory location here. So how do you instantiate this? How do you use loads and stores to put data in there? And how do you minimize chip memory? Because it doesn't make sense in this case to have 1 gig of on-device registers and then it's just mapped over. That would be inefficient. You wouldn't even need the external card then. So how would they possibly make this peripheral work? So why don't you take 30 seconds, talk amongst yourselves, come up with some answers, possible answers.
Bus, I'm assuming, let's say at this data, this piece at this address, store this data, or
I'm Marshall. I'm Gaba.
An external device and a person.
Since the SanDisk,
I mean,
at least the
definitely
first
is
lecture
memory
was
driven.
talking about how it has its own like
It's something, but external devices like
SD drive. I would assume that like using
like an SD
Wait, what's
Yeah, basically I synthesize it, it works, I synthesize it for a smaller clock period,
I feel like external devices, like
and I keep going down until I fail.
I guess like
Because you only should be within a data set.
there's certain memory addresses where you're
it's like filling
there's an address you want to put it on the storage.
I'm not entirely sure.
You want to put the data.
All right, so what do you think? What are some ways to implement the memory space here that's called external device?
Use like shift registers and shift in things, so you don't have to have like one address for everything. You can just keep shifting in different numbers.
Okay. Anybody want to expand upon that idea a little bit or come up with a different one?
It's a little bit of a different one, but
Go ahead.
maybe there's like an address where you can put in the address you want it on the SD card, and then an address where you can put the data you want to put it, and like on each clock pulse, it updates that address.
Yeah.
Maybe some like read write bits.
Okay, those are kind of similar ideas. You're talking a little bit more about the address and he's talking a little bit more about the data itself. Any other ideas? Okay. So as I alluded to, it's not going to be a gigabit's worth of external memory or internal memory. It's not plausible. So in this particular case, they just have a finite state machine, right? So the state machine will sit there and respond to, I took it away, like this address space, whatever's in these addresses. Maybe I should go up to here. So this external address space, so that's right, A to F. So A to E, whatever this address space is, it'll say, well, if you're trying to write information to me, well, I'm going to take it, I'm going to store it on the SD card. Okay? I'm not going to necessarily store it locally, have a complete copy. So this is going to be a finite state machine looking at addresses. Oh, you're talking to me. Okay, what's your data? Push it over there. And now we're going to talk about the mechanisms to get that done. Yes. So memory mapped I/O. Talked about this a little bit. There's two basic types. So there's peripherals and hardware registers at a given address. So there's literally a copy of that memory or a version of that memory on the device, or there's a virtual state machine, or a state machine that has virtual registers or virtual memory locations. All right. So at the end of the day, from your point of view, or at least the core's point of view, these are just loads and stores. All right. So I see some confused faces. What questions do you have? Some faces, yeah.
If we were writing the ARM instructions to deal with like these external devices, just to make sure like we never need more than LDR, STR type.
That's it. From your point of view as a programmer, that's easy. You already know the instructions you need to do. The problem is that what the instructions mean, that's in the data sheet. So if you, what the data that you're loading and storing in means. So remember that you had to go and configure your GPIO registers, which means you had to go read through the data sheet and say, well, what does this memory address really mean? If I put a 1 or 0 here, does that configure the speed or the output type. So if you're going to do an external device, you might have, I haven't read through the spec for external memory, but I'm going to guess there's some configuration registers that say this is the address range, or this is how big the external piece of memory is going to be. And you probably have to set up the GPIO pins. So in a sense, you already know how to enable and work with every single peripheral we have. The problem is you have to read the data sheet to know what the data is supposed to mean. Other questions? Yeah.
Could you clarify what's meant by virtual registers?
So in this example, the core can write to a gigabyte's worth of memory locations. There's not a gigabyte's worth of registers here.
Okay.
Right? It just wouldn't be cost effective. So instead, it says, the core says, I'm going to write to this address and put this data in here. And then I'm going to increment by 4, let's say, another word, another word, another word. But inside this pretend state machine I'm making up, there's only one, say, register. And it's just keeping track of what address. Whenever the is saying store word here, it says, okay, I know what to do with that. I'm going to take the thing, put it in a shift register, let's say, shift it out into external storage. And then it says, oh, I want to load. And it says, oh, you're talking to me. So it looks at the address space and says you're between A00 and AFF. It says, okay, you're talking to me. Where do you want the data from? It says, okay, hold on a second. It goes out to the memory, gets it, and then hands it back. But there really doesn't need to be a gigabyte's worth of registers in there to get that done. Yeah.
Wait, so to clarify, like you can't have more than a gigabyte of external like peripherals for this processor?
Correct.
Okay, that makes sense.
Well, ARM has pre-allocated gigabytes worth of external memory. I bet a clever person could figure out how to get around that. I'm just saying that this is what they've done. Yes?
Can you go back to the how the memory is laid out?
Well, with this iPad, I hope I can. We're thinking like this slide?
Yeah, this slide. So the external device was the SD card, right?
Yeah.
So then on the actual, on our hardware, there's nothing there, right?
Correct.
So my question.
Well, there could be. Go ahead.
So why did we put the system on top of the external device in memory? Because to me, it's weird in the sense that if I have a 1 gigabyte, or let's assume I do a 0.5 gigabyte SD card.
Yep.
And I write to the address that's past the 0.5 gigabyte, but below,
Sure.
So what would happen?
Nothing. It will. So there, if we look several slides ago, we saw these things it's called reserved. So you saw these memory locations where it's there's SRAM and it's reserved. Right? Reserved means not there. Reserved means that the manufacturer says, well, one day I could add something there, maybe in a future spec or something, but there's nothing there. So in the best case, well, your compiler should throw an error, right? Saying look, that's not as an out-of-bound memory address. But say you're very persistent and clever and still want to write, maybe you're doing assembly or something, you're trying to write data there, nothing will happen. Yeah.
I might not be understanding this correctly, but if we have a gigabyte of external device space here.
Yep.
Why do we need it? Why do we need a full gigabyte to store to a full gigabyte? Why can't we just use that gigabyte?
Because that gigabyte doesn't actually exist. It's a gigabyte's worth of addresses, worth of conceptual locations to put things. They've pre-allocated and said A00 through AF000 is where you could store things, but the mechanism is not on chip. Davis, right?
Yes.
Getting it.
Are the mechanisms for the other components of memory all actually physically there?
No, sometimes. No, and sometimes and yes. Okay? So if we remember SRAM gives you, I forgot, half a gig of RAM, I think. But your microcontroller doesn't have it. Your microcontroller only has 64K.
Also just
It's just reserved. It's not available because ARM here is trying to make a spec that works for any manufacturer. Right? Remember ARM's business model. This impacts how this works. So ARM is saying, hey, I want to make a ISA and architectures that work for everybody, and I'll let STM or Apple or Cypress or whoever make a chip that has up to this amount. So that's why you have to kind of look through your data sheet and see what's actually available.
It's at 0.
Does it really 1 gigabyte for external?
Yes. I mean, you could get, that is if you're going to use the load store mechanism where you just have addresses. Now, we could create a chip that says uses a UART peripheral and have another mechanism for sending data. I'm just saying within the confines of how this chip is laid out, loads and stores, it cannot accommodate more than 1 gig. That's it. You want something better? Go to a different architecture. And this is the same if you remember, maybe you don't remember, but we had 32-bit systems. That means RAM was capped at 4 gigs. That was it. This is the most space you could get. And then we went to 64 so we could have larger RAMs. What do you think about that? Okay.
11 or 10 home cap at 128 gigs of RAM, but like Pro is like 2 terabyte.
Because they want you to pay more. I don't know their business model. I don't think there's a computer science reason or a computer engineering reason. I think that's a business reason. Okay. All right. So how are we doing? What other questions we have? These are great questions. Let's see. Any other questions? All right. Let's talk about buses for a little bit. Right here. All right. So did you guys talk about buses in 270? Kind of. Somebody says maybe. All right, so buses are just sets of wires that transport data. There's 2 main types that we'll learn about. There's a parallel bus, which means you have D flip-flops here, D flip-flops here. On every clock cycle, data is latched in here. So basically, you say on the negative edge, you would instantiate the data, positive edge, you clock it in. Whatever your scheme is, you have n number of bits going in parallel. So it's very fast, but it also takes a lot of space. As is opposed to serial, which is just over time, you will do highs and lows over time to load data over here. So here it takes 8 times longer to send the same byte, but you only needed 1 wire and one pin for each device. And so this is predominantly used on chip, and this is predominantly used off chip. So later on, you'll be talking about SPI and I2C and these other protocols which allow you to talk chip to chip. Well, in this part of the lecture, we'll be talking about the high-performance bus. Does anybody know why on chip you have parallel and off chip you might have serial? What would be the reasons for that?
Don't want.
Luke, right?
Yes.
Getting it.
Don't want like a ton of pins or wires going off chip.
Yeah. So if you look at a chip and a die, like getting signals off and on are the hardest part. Not hardest. They're just limited space. You just can't have that much room for I/O, and so now you become limited in I/O. Why is that not a problem on chip? I thought chips were supposed to be small, and this thing's big. Yeah.
The wires can also be really small.
Wires can also be pretty small. You're not limited by pins on wires, and usually these can float above the transistor. So there's good reasons why it's easier to put parallel buses on the device. So we can look at an example here. So this is Intel 8008. It has all the things you would expect. It has ALUs and registers and instruction registers and program stacks and all those sorts of things. If we go and look underneath and we look at the bus structure here, see blue and red are power. That kind of makes sense. It's got to be routed everywhere. And then the rainbow colors are an 8-bit bus. And so somebody one year asked me, why do you keep talking about buses? Why are you making it so difficult? Just put the registers next to the memory and just be done with it. Why do you need a bus? Well, the reason is it's actually not that close, right? And you do need a structure to do this. And you really need to be able to talk to multiple things at once. It's not just that I'm doing a point-to-point. It's that there are many things that could get data on and off this bus. So you need a more advanced structure than just 8 wires going from one location to another location. You can look through the slides. I mean, again, they're online. If you want to go play with a bus structure, this is an example of it. So this is a clock. It'll be counting up, and that just displays whatever the count is. And here you can see how it's clocked over, and those are just 8-bit DFFs. So the link is here, and it should work for you guys. Okay. So we talked a little bit about this. The reason why we have it is there's lots of different peripherals. So we have, we're not really going to talk about the advanced peripheral or the high performance bus here or the matrix in this class. We'll touch on it briefly, but we're going to talk mostly about the advanced peripheral bus. Once you understand this, you understand why this exists and what it's trying to do. It's just, they're just a higher performance version of it. So we're going to focus on this, how this thing works and how it allows us to push data around. So my question for you is, let's see. So here we have initiator, a target, let's say. Oh no, I'm giving it away. I shouldn't have done it. I was gonna ask you what else needed. Oh, I messed it up. All right, fine, you guys saw. All right, what else do you need? So is data enough? No, data is not enough, right? So you need to know address. So you need to have some way to encode address in here. You're going to need other things like clocks, and then if pretty soon you're going to need control lines, like is there an error? Do you need to be waiting? So there's all these other things that go into a bus structure. The addresses help you talk to different targets. So in this version, this is different peripherals. Yes, what questions do you have? Yeah, Luke.
When you say two targets, is it just sending all the signals at both targets and then the targets will figure out whose is whose?
Pretty much.
Oh, okay.
Now, some methods you could use is targets could have addresses, and so the target only pays attention when the address is there. You'd have control lines, which we will see, and control lines can say, I only want this target or this target to respond. Yeah.
So you said that it was 8-bit buses?
For the Intel, yeah.
So how do I do like 32-bit register? How does that data propagate?
So that's a chip that's over, whatever, 40 years old. So for ours, it's a 32-bit bus.
Oh, so it's the length of the register.
Yeah.
Oh.
Yeah. In the class, we're just going to say that all the addresses are 32 bits. In reality, you don't need that many because there's not that many peripherals. So there's usually a state machine like in here. So you would have your core is going to send load and store commands to the initiator, and then that's going to go and send them to the target. Well, you don't need 32-bit line of address to get that done. But for this class, we're just going to assume, we'll make things easier. We're just going to assume it's all 32-bit addresses. All right. Any other questions? Yeah.
Okay. But if your data, like you're transferring a register's worth of data, right?
Yep.
That's 32 bits.
Correct.
And if it's a 32-bit bus,
correct.
How do you have room for everything else?
Oh, there are extra lines.
Oh,
so when I said 32
isn't like the whole thing.
Correct.
Okay, sorry.
So we have, I'm stuck in nomenclature that assumes that you've been working on this for 20 years. That's an assumption of how all embedded systems work. We just assume you know enough until you do. So yes, a 32-bit bus usually means the data width is 32-bit, and then you have extra control lines and all these other things. Yeah.
So because it's a parallel bus, we're saying that there's going to be 32 bits on that data line.
Yep.
You're going to go clock, ka-chunk, and then it's in the target.
Yep.
Cool.
Except there's more, don't worry. But that is the exact right thing to think for what I've taught you so far. There's a few more steps. Yeah.
How do you ensure that initiator and the target can run on the same clock?
They share the same clock explicitly.
By design, they can run on the same clock here.
Yes. So you may not have explored it yet, but in CubeID, they have the whole clock tree system where you can go and tell which clock you want where. So you could, generally the advanced peripheral bus or high performance bus runs at like 120 megahertz on your chip. And then the other ones I think run like 80 or something, but those are configurable. We can assume for this world, for this example in this class, that they're always a synchronous bus, which means there's a clock, and that they are correctly locked in time, right? There's no like 2 clock worlds that have to be negotiated.
And the address bits just tell the data where to go within a target, right?
Correct. And for simplicity, we could just go all the way back to our highest level thing and say that the address bit is actually the address that the core thinks it's sending data to. It'll just make it easier. But if you don't have that many targets or that many, you don't have 4 gigs worth of address spaces, then for economics reasons, you just wouldn't use all 32 bits of that address. Okay. So this is the idea in the abstract. We always terminator or initiator and target. Sometimes we use controller and peripheral, depends on what we're talking about here. Other documentation we'll call bus masters or slaves. Unfortunate naming conventions, but this is what our industry does. When you get in control, you can name it anything you want. Maybe you'll choose things better than master and slave. That's what the industry has used for the last 40 years. All right. And you'll see that in your documentation. So this is literally what's in the Advanced Peripheral Bus spec. You'll see it for some companies use master and slave for their I2C buses. Other companies are moving away from that terminology. So let's see, some high-level ideas here. The target, so the targets typically cannot transmit on their own. They have to be initiated or allowed to talk by a controller. You need some central controller to say, okay, it's your turn to talk, your turn to talk. Otherwise, you have multiple things talking at once, you get collisions on the bus. We typically use tri-state drivers, which just basically means that peripherals or the targets have a way to completely disconnect, electrically disconnect themselves from the bus. So say you're trying to send out data, you're not going to collide with other people's data. Some of the wires, like we'll talk about, are going to be shared through all devices. So all devices will get the data, but they might not get all the control lines. Yes, just to make it explicitly clear, core stores data in here. You have some initiator or some controller that basically has a finite state machine in it. It's saying, okay, you gave me this instruction, okay? Now I need to turn it into a mechanism which will transport data across the chip, which means I have data, I have clock, I have control lines, I have address, and then you have some target over there that's saying, okay, this is like the bus inside the peripheral. Let's say you're talking to me. Now I should go and update, say, the output register with some data. So before it was just the idea that we have the core is going to put loads and stores into some place in memory, which it does, and this is the mechanism in which we're going to push data across the chip. Yeah.
I've heard about I2C buses a lot.
Yep.
Are those the main ones that we're going to be using, or where do those fall into?
Good question. We will be learning. So I2C, I forget what it stands for at this point. Integrated Communication Protocol, something like that. That is a serial thing that for chips to talk to other chips. So that's a way to get data off chip. We'll also talk about SPI, serial peripheral interfaces. That's the other kind of competitor or alternative method, and that's also for chip to chip. And there's UART as well.
Okay.
Well, if you when we get through all these lectures, you understand this, you'll be like, okay, I understand why. Well, it'll be easier to understand why I2C is making the decisions it is. Okay. Any other questions? Okay, so now we'll talk about the specific mechanism that occurs on your chip. So that's the ARM Advanced Peripheral Light Bus. All right, so there are two buses. You have the high performance bus, low performance bus. They're really just versions of each other that have been slightly optimized. So the Advanced Peripheral Bus, lower power, simpler interfaces. Really, this is just tolerant to latency. That's really because you have these things, these peripherals, they're really slow. They're waiting for humans to push buttons. Humans take millions of cycles to push buttons. Humans are horrible. The high performance bus, as it says, it's much faster, it's pipelined. So you can get multiple communications going at once on the bus. For this reason, we're not really gonna deal with it. There are multiple masters or initiators. We'll talk a little bit about that when we talk about DMA, and they'll all have to work together. This also allows you to have priority over some peripherals have higher priority than other ones. You might split your transaction up. But today we'll just talk about the Advanced Peripheral Bus. All right, so from our diagram, that's really just this. There's a bridge that goes between them. You'll see that in your data sheet. And we're just talking about the interactions between the Advanced Peripheral Bus, which is the controller in this case, and the peripherals. So this whole bus structure is what we'll talk about. If you get real excited, this data sheet's only like 100 pages long. You could actually read it. You'd have to be really bored. I understand that. But you could actually read it. All right, so some notations. This is probably just good to reference to later, but I'll try to explain what some of these things are. So we have the common clock that you see here. Then you see the high to low translation has this kind of gray section. That's just indicating that we don't know from a time diagram point when it will actually happen. It'll happen somewhere, but it's not a precise edge that occurs. You'll have, let's see, buses that are high impedance if it's in the middle. That really won't come up the case. This is saying that you have a bus that's changing, and this means that there's more than one bit of information. So that's a clock. So this could be like a 32-bit bus, and it's saying that there was some amount of data, the data changed, and now it's some amount of data again. All right, so for your advanced peripheral bus, you have a clock. Ooh, fancy. Clocks usually work on the positive edge. You have an address. We're just going to say it's 32 bits. We used to do a chipset called Smart Fusion, which actually had an FPGA and an ARM Cortex-M3 on the same piece of silicon, and you would write your own drivers, and that tool chain was horrible and hard to use, but you could actually like make your own peripheral. It's pretty cool, and that only had an 8-bit address, just as example that you don't need 32. You have a control line that simply just says if you're writing to the peripheral or reading from the peripheral. So if it's high, you're going to write. If you're, and this is from the controller's point of view. If it's low, it's going to be reading. It's going to be pulling data out of it. And then you have the data, which is 32-bit long. Usually we indicate it as there's some value in here. So we'll tell you what it is. Obviously, you don't know what it is here. You just know that there could be 32 bits. It changed, and there's some amount of data. Then we have P-ready, or P-select, sorry. P-select selects a target. So it's a dedicated line that tells a target, you are the one I'm talking to, not this other target. So that as an individual line. P-enable is there to enable the peripheral. It's not to turn it on, more to say that, hey, the data is ready, you have been selected, now is your time to act. Oh no, sorry, that's what P-ready is. P-enable, sorry, is to enable. P-ready is to say that all the data is instantiated and is ready to act, and you need one clock cycle between when the data changes to when P-ready can go high. You certainly could design the bus in a different way. The designers have just chosen this so that there is some margin there to ensure that the data has been instantiated and the peripheral can react.
Is P-select like the number? Is it 1 bit?
Yes.
So
how are you wired correctly, like so that you know what target you're talking to?
Let me get there. There are multiple wires that go to each target. So, but we'll get there in a second. Is there another question? Yeah.
Yeah, I'm a little confused as to like the need for P-select and P-address, where wouldn't the address determine what you select?
Yes. So we could, I mean, you're absolutely right. This is a logical, you could do this. I think the architects wanted to make it very explicit. And now you can say, you can have a peripheral only respond. So the peripheral might have to have logic internally that would decode an address. And so you might not want to have your peripheral decoding all 32-bit or all 8-bit addresses. Instead, you say, if you turn on, I select you, and now you only have to look at certain bits to know what to do. So that reduces the complexity of the decoding process for each peripheral. I'm not a peripheral designer, so I'm just kind of theorizing here. Whether, yeah.
Wait, so P-ready is sent not by the initiator, it's sent by the peripheral that tells initiator you cannot initiate.
Oh yeah, you're right. Thank you. P-ready is, sorry, that's why it has to happen a clock cycle later. So the target or the controller instantiates things, and then P-ready says, I am done with that data. It could be that you've made a request for, I don't know, go get an GPIO pin or do something that takes a long time. P-ready is a way in which the peripheral says, okay, I'm not ready to give you my response yet. I'm not ready to do the thing, so I'm going to hold that down. And this happens because sometimes the core is going at 120 megahertz, or the controller, but the peripheral may be at 60 megahertz or something slower. So this is a way to kind of synchronize in time. Even though the clocks themselves are synchronized, you still need to say that the peripheral, which is much slower, may need more time. Thank you for pointing that out. Does that answer your question, or I just start more questions?
The peripheral tells the initiator it's ready to read or write.
It's ready. It's done its command. I've clocked in the data, for instance.
Oh, so it's just ready for anything.
Yeah, well, so we'll go through some examples that will elucidate that more. And there's a state machine at the end. If you really get excited, you can work through all the little logic of it. Any other questions? All right, so let's walk through an example here. So what's happening here? So here we have some controller has gone through and said, okay, I'm going to instantiate some data. So it says, here's an address at time T1, here's an address. I'm going to write in it, so write is high. I've selected a peripheral, and I put some data on here. Then it has to wait one clock cycle. Because it can't say, okay, clock that data in now. It has to wait until all this data is set up. So basically, you have a whole clock cycle to instantiate the data, get it stable on the thing. Then enable goes high, saying, okay, now read this data, okay? And then it just happened to be that the peripheral was ready immediately. Like if you're just going to clock data in, it will say it's available immediately. But that's the response. So let's walk through an example. Yes. Okay. So here, I forgot your question. You were asking, how does all this get wired together? Okay. What's your name? Andy. A-N-D. It ends with an I, right? Yeah. All right. I'm gonna one day. That can be my final exam. I can go and see if I can know each one of your names. Okay. So P data. This is a 32-bit bus that goes to all the peripherals. Okay. That means that all the peripherals see the same amount of data. You just have to know when you're supposed to respond. You also, to all the different devices, you get the P write. So you have one pin to say if it's a read or write, and the enable. It's the P select. Oh, and then the address goes to everything. It's the P select, which is individual. So there's N P select lines for N targets, and the P select lines will, as individual line that says, this is the target I care about. P clock goes to every device, so everything's synchronized. And then in this particular, now this is not required for serial bus or parallel buses in general. This is just how ARM has instantiated the Advanced Peripheral Bus, is that every target has a 32-bit bus that goes back to the peripheral. So they have their individual buses. Why would an architect make that choice? You're just wasting lots of wires. Why would we do this?
Read and write at the same time.
Okay, that's not bad. Not exactly what I was thinking, but that's a very valid reason.
In case you need the data that's getting outputted by some of those targets back in what you're going to initiate.
Say that a different way.
Sorry. Like in case that data that's being outputted, you need it for another input. That's like, yeah.
Yeah, okay. But why do we need to have, maybe your statement answers this, but why do we need to have why does each target need to have its own bus to write back data to the thing?
Because they could both be writing at the same time.
They could both be writing at the same time, yes. And I think one of the ideas that you shouldn't know now, but could have guessed, is that these things can be on different time scales. So it could be that the APB bridge says, go out to this timer and tell me, or I don't know, yes, let's say a timer. When the timer goes off, then send me back the data. So on some period of time later. And then it goes to, while that's happening, then the target goes, or the initiator goes off to this target and says, give me some data out of this other device, or go out to a GPIO pin and tell me if it's high or low. And so you don't want to have bus contention on these things because they're happening at very different times. So the Advanced Peripheral Bus is very tolerant to slow things and things that happen at different times. That allows this target to have full control over and get his data or her data all set up here perfectly without messing something else up. Also, these things can be at much slower clock speeds than this one. So it may actually take, 100 cycles to get this thing to actually get the data instantiated on its bus, and you don't want that to clobber other people's bus or slow the system down. Yeah.
Why would there need to be a P enable to each target when couldn't the P select kind of just do that as well if when it's selected it's enabled or?
It could. I mean, there are many ways to architect a thing, so it's possible. I think P enables just says that we're going to turn on this entire target. Let me go back here. So P enable is basically saying, hey, I'm going to enable the target. In this concept, it means enable it saying that the data is ready. This is the time, at this specific time, you should listen and pay attention to your inputs. But you could have, I guess in this context, you could talk to multiple targets at once. So say, I can't imagine exactly when this happened, but you could select multiple targets and send the same data to multiple targets. So that might be a reason why you don't want to separate P-enable from P-select. It's a good question. What other questions do we have? Oh, and P-ready. Excuse me. P-ready is a signal that comes from the target. So there's individual P-ready lines, and P-ready is kind of a synchronization just as much as P-enable is. So this synchronizes and says, hey, initiator, I was spending a bunch of time getting my data ready. We don't know when the data on this bus was valid, but when I raise P-ready, the data on this bus is valid, or if it was a write command, I've gotten the data, right? So imagine that the initiator is sending data to the target, but the target is very slow. Well, it needs to say, okay, now I've actually clocked in that data. Now you can move on to the next task you're going to do. So it's a way to synchronize between these two different things. Yes?
Does the initiator read off the same clock that it writes on?
Yes. Yeah.
It's kind of like P-enable and write data correspond together, and then P-ready and P-read data correspond together.
Hold on, you're going too fast for my slow brain. P-enable.
So P-enable and write data correspond together. When P-enable is high, then the target should.
Well, you could. Write data is telling it which direction it wants. I want to read data out, or I want to write data in. So it could be. This has. Remember in our example, we had the lowest A register that was D flip-flops. I want to read a value out of this thing. So it's saying this address, this particular peripheral. I want you to give me the data out, and then it knows it's supposed to send the data back here.
Okay.
So, if P-write is on, who's sending this?
It's all from the controller or the initiator's point of view.
Oh, every terminology is from the initiator.
Yeah.
So P-ready actually starts from the initiator.
All right, you got me. Hold on.
P-ready.
Okay, so these are supposed to be inputs. Those are outputs. Write and enable are from this person's point of view, like you are enabling that thing. This is saying that the peripheral ready? Yeah, it didn't really work. Yeah, except for P-ready. That comes from this thing. Okay, so we're gonna go through an example, but let's just, let me see here. Let's just make this explicit. So here, in this example, we're gonna have two devices. Don't know what they are, but they're located at these memory addresses. So device one, so say it's a peripheral, has 1000 to 1000F, and the other one is 1010 to 1010 1F. And so we know those things exist. We're going to say that your core already has some data in its register, and then we're going to do a store, okay? We're going to store R1, or the memory address that's located in R1, and we're going to take the data and put that into that address, +4. So if we go back to a couple lectures ago, that's going to look like this. Oops. So we're going to go, R1's going to go find this address, but it's that address +4. All right, so this is the address we're looking for. And then we're going to take the value in R0, and we're going to go place it in memory over there, which happens to be device 1, right? Because this is the memory range. Forgot to put it over here. But this is defined to be the memory range of device 1 versus device 2. Okay, so that's going to be in device 1, and we're going to store 2000 in there. but it wasn't supposed to be 2,000 because I made these lecture slides yesterday. It's supposed to be coffee. Okay. This is the actual value in R1 for the example we're about to do. Okay, so that's happening there. So what I'm gonna have you work in groups is figure out, write down, draw what the bus lines here are gonna be. You know what's supposed to be happening, putting loads and stores out there. So draw the bus lines of what's going to occur. Oh, you only need 3. Thank you. That's enough. A bunch. Okay. Feels like the right number. Because it's real packed up here. You guys are real scared of me down there. Yep. You're running out?
Well, yeah.
You got any extra?
Driver's test.
Nope.
Yeah, she's a senior in high school.
Got any extra? Thank you. Oh, you need, uh-oh. Yeah, it's worse. There's a front and a back. You guys are in big trouble. We're gonna be thinking today. It's awful. You guys can work together. You can, if you don't have one, just write both names on it for your partner. I think the printer had some problems. Does anybody have an extra one? Just write your name and your buddy's name on the top of that. We'll give you credit. All right. So draw those bus lines. Here's the, if you get real excited, this is the nomenclature if you needed it. And we're going to assume this is R0 has coffee in it and not 2,000.
So we're storing.
Add 4.
Does that mean your address will change
to some stable value, right?
So
Yeah, my question was, is it 4 bytes? Like, is it actually adding 4 to the number?
For the top one, P enable high for.
I think it's never gonna get enabled, right?
Or D.
So that was.
I thought P enable is high driving the transaction. It's high during the transaction. I think.
Because I don't wanna do this in bed.
It's when the write is ready to occur, not words. Is it not on the slide?
I don't think you put P address.
Yeah, but like per cycle event transaction.
Select never goes high, so.
It splits to every single.
Oh, so you know, and then you just have to check.
And then P select is unique 1004 device. Same with P.
Or you just essentially copy that's P ready.
Oh, here.
That's what everyone's saying.
How you know what the
That can be high.
Okay, so P address.
So, like, what's up with the state machine? Because if we're talking a device, so there's only one store command.
Or what are we thinking?
Do you think you're better at drawing, or do you think I'm better? You can erase yours.
With the other inputs still.
I might have an
Enable is always low, so you never actually
It's gonna like cross over.
What's the?
It is the.
We're talking to device 1.
Because that's what they're doing here.
Like the shows, you have to do the addition.
Yeah, just 1,000.
The first transaction.
It's actually 1,004.
So you have to like apply remote numbers, right?
Because what's happening?
What are you guys gonna do?
weird ratings.
Storing, yeah. The question, like, when does it go high? Sure.
Okay, so like
0, like, when is T0? Like, this is not.
Yeah, okay.
Just take it.
could draw that in there, and right.
P right also goes to the parallel bus.
Oh.
You have to read from this address.
I think that would be.
Can you give me the paper?
What was this next?
I don't mind, it's up to you.
Okay.
Yeah.
I don't keep
Which ones do you think need to shift to select and right, or?
Address.
I think it's definitely after you put in the address.
Kind of right to it, right? So.
I'm assuming it would be when
Oh, so you think that means enable and ready to go one more?
No.
At the same clock cycle.
Because I think it's
Sorry.
that's a different device.
Nope, just sign your name next to somebody else at the printer. Got away from me today.
Okay, thank you.
But P enable is also.
These diagrams. So I'm assuming it'll do basic default filters unless you
Has to wait for P ready.
This.
Do we have a concept?
My partner.
Or do we just assume it's ready automatically? For
It's copy, right?
Is that,
I can say one clock cycle after the
I mean, that is what they have.
just because that's what they
It's
what
P
they
right
do
above.
here.
thank you.
Okay, so I'll just do the same thing.
Yeah.
We don't know that it's like stable until.
Yeah.
That's what that's
But we should.
means unknown.
It's funny. I also went home this weekend with my younger brother.
Unknown. Unknown.
He's
It's his birthday or something?
no,
P
he
cell.
graduated.
No, because P cell is ready.
It's our data.
Like Moss. No, I don't get the
P ready is
would
the
be
same
a
thing.
freshman this year. He graduated high school.
Oh, this is a different device. The top one is.
What would be different between D1 and D2 in the timing diagram, and what would be the same? So this diagram tells you what's the same between the two of them, right?
Oh, we're
So-
is he like traveling somewhere?
Target 1 in this thing wheel gets address, right? And so does target 2. The address data should be the same for both of those devices because they're both connected. Right? So address goes to everything. But some lines don't go to everything. We're talking about the bus that goes to the target. Doesn't even know if it's supposed to respond yet. So the target's going to get all the data.
Well, not
All the signals going to it.
Are you doing same something like P cell is always gonna be low?
Thing and trying transactions on the first cycle.
is when you have both P cell and P ready.
No, P enable is searching. So I'll just draw the same thing.
Enable and ready.
Yeah, that was just.
Right, because it selects the only one. Go to every single.
So, enable still go high in D2 because
It's not gonna be ready to just
enabled, so that means all of them are enabled?
No, because P enabled are.
Yeah, okay, I know.
There's no concept of this, I guess, so like.
You can assume the peripheral is enable and ready, or enable and ready are the same.
I don't know if P ready will go up.
It is a thing. Okay, perfect. Is ready determined?
Oh, for the
Ready is given by the target.
About if P is enabled, right? You only care about it if it's selected. So it's like, I guess it's minimizing.
Enable turn. So what causes the enable to turn off? What causes the enable to turn off?
No, I just
Here said, okay, I'm done. Right? And how does it done is because we enable occurred. So
It would be like, it would be a lot of.
Like how the
Like really care about it if it's selected.
And this is
From this perspective, it doesn't make sense. But from the perspective of like minimizing number of lines.
No, it's undefined. It's got the high and low.
we don't know how it works.
And the text
It's like, this is how this.
Happens to be 0.
Select and ready.
device would just be loads of
Device.
Yeah,
Because you assume them
Yeah.
peripheral, you're like, right, that looks like.
Oh, yeah, we can do the address. T2. Oh, T2, yeah. When enable goes.
He's like
Columbus.
So P address between T1 and T3 is what we agreed, each at the end of T3.
So I don't understand what happens at T3. And the P cell and P enable allowed to go to 0 because P ready went to 1.
Correct.
Okay.
Address line. This thing will happen, so is different though.
I would give you one
data.
Read data on this one? No, there isn't.
These are output from the target, so and over here P cell and P enable just
I don't necessarily love doing this in the head, or for the top one it's this, right?
Something like that, but for the bottom, do you think it's gonna be just low, or do you think it's gonna be high and low as well?
Okay. In there, let's see what happens. All right, so what is address? What is the value on address? So remember, address is a 32-bit bus. We're gonna represent it as 2 lines. We're gonna write in the data. So what data should we put in the address? Talk to some of you.
1004.
1004, great. And because it's store, we did a store command, which was the value for the address that's stored in R0 plus 4. Okay, that's going to go there. Oh, put together. Okay, what about on D2? Yeah. The same. Yep. Nope, but I didn't show that. That's fine. We'll get there. I forgot my own builds. Okay, so P write. Why is it a write? Because it's a store. So remember, this is from the initiator's point of view or the bridge's point of view. I want to write data in, which is the same as storing data. So that's why write goes high. And in this nomenclature, we just said that we just ignored T0. We said, okay, all the transactions started happening at T1. If you drew it over here at T0, it doesn't matter. It's still fine. So here's all the instantiation is going to occur, right? So the bus changes, write changes. What's P select going to be for D1? 0. P select should be something. P select, because we're trying to write to D0, right? Because this is in the memory address range of D1. So we're going to select it. We have an individual line that goes to each target, and so now we're going to say, okay, I select you. What about P enable? When does P enable do something?
At the start of T2.
Yep, in this diagram at T2. So the initiator said, okay, I've instantiated all my data here, and now we're going to, once it's ready, then we're going to go and tell the target, enable yourself. I mean, it's always on, so that's a little bit word, but this thing is ready to act on that data, okay? And then the data here is coffee. So coffee was the data was stored in R0, and that's being stored into this memory location. And what happens with P ready? P ready.
We could assume it happens with the exact same. It's like it's ready right as enable happens.
Yep. Now, we haven't talked about, this is the hole in the problem, because we didn't tell you all the specs of the peripheral. Okay? When you get it written, P ready occurs sometimes later. You say, oh, this is a really slow peripheral. But we'll just say, okay, in this example, P ready is available immediately. Say it's a D flip-flop or something. You're just latching in data. That's what you're supposed to do with this. Well, it already happened because you locked in data. It's available immediately. Yeah.
Quick questions. What determines when, like in P write and in P address, what determines when they like transition back to a I don't really know what it is state? Like, because I know in the
when do we start the next bus transaction, for instance?
Yeah, I mean like in there it's like it transitions again, but in the slides it didn't transition again.
So P ready has gone down. Yeah. And say I'm done, and now the rest of the bus can go do whatever it wants to do.
So
We know the state machine. Would it be reasonable to answer the question and just, there's just two lines that should be later than everything else, which is P ready should be a X time later and P enable should be a certain time later.
P enable should be at least one clock cycle later. P ready can be at the exact same time as P enable or later. And you know, we're getting into the world here in the sophomore or junior class where things are gonna get ambiguous. So if you get to an exam and you're like, you didn't tell me how my peripheral works, how do I know? Just write assume. I assume it's ready instantly. There you go. We'll give you credit for it. All right. Any other questions on D1?
Does P enable have to come later than P select?
This is what the bus architects stated. This is how they want their spec to run. So does it have to be? Is this the only way to ever write a bus? No. But they're just saying, I want to ensure all my data transitions occur and they're not, right? If I made P enable here, well then you might be trying to act on data that's changing, right? So you want your data to be clean, stable before the peripheral starts acting. So they instantiated a bus or a 1 clock.
Is what dictates when all the other ones.
P ready is basically saying the peripheral is done, has accomplished its task. And it can go low and it lets it go, or the initiator can say, well, you've done it, you already instantiated ready high, now I'm gonna go and do something else.
The step of creating an architecture do the people decide where they want the ambiguous stuff to like
the ambiguous stuff, but like what does D1 do and when is it ready?
Like it's like there's things that different between architectures. Like when people like make architectures, do they like make these things different like near the beginning or like near the end or like all the way through, like stuff like that?
Well, I'm not an architect. We have architects here that do architecture research. I would say that to answer your question as a high level problem is you should understand the architectures well enough to choose something based on trade-offs, right? And you say, all right, I want this style of bus. And then I'm sure at the end of the design, you're like, oh my gosh, there's all these edge conditions and life is horrible and nothing works. And then you're trying to tweak the design. But usually you should be able to choose the general bus architecture at the beginning of the project. Does that answer your question? All right, let's move forward here. Well, okay, I already gave it away. Address is going to be the same. What about P right?
Same.
Okay. Good. P select. Oh, yeah. P enable. Yeah. It just happens that the target here knows. Don't pay attention. You didn't select me. Don't pay attention to this line. Okay. P write data. Okay, yeah. And then P ready. Doesn't matter. It's not talking. It can be high or low. That's all this thing is saying. It's ambiguous, but it's saying high or low. We have to do not care because we're not even being talked to, so it doesn't matter if I'm ready. And then the key takeaways is just what data. These are the things that are actually different. There's only 2 lines that essentially are different between the buses in this example. Yeah.
Why the P right did you have like oh never mind. Okay.
Well, answer.
Well, I see now because like why is P enable and P right? Like, you're going from low to high, but they're written differently. Like one has across the top.
Oh, here?
Yeah.
This means I don't know what it is and I don't care.
But for P enable we know it's low.
Yeah, P enable has to be defined.
So P right was saying we're going from I don't know, I don't care to high.
Yep.
You'd not technically be wrong to omit all of the like blocks on the right side where they transition back to don't cares. Like that can happen at any
You could admit this. We didn't say what the next command was going to be, so maybe there's no next command. So you're saying like all this line?
Right.
Yeah, that's fine. If I told you here's 4 commands, then yeah, you'd have to instantiate all 4 commands. What's that?
Wait, what does high mean?
Oh, computer scientist? Computer engineer.
Is it like the same thing as when it comes to electrical? Like when
High impedance, this means the bus is not driven high or low. And so the state is not known and we can't rely on it. And that's why it's just in the middle. I don't know why they chose that. No. I see people taking photos. All the things are online.
If we have like multiple instructions,
How would we know how long?
Data gets in,
Like how long is this here for? Well, you probably have to be told something about how the device is going to operate.
Oh, okay.
You would, maybe I'd say something like, device is ready immediately.
But we'd be given that information.
You would have to be given that information,
Okay.
yeah. Or you come out in the exam and tell me, and Matt, we've, messed up something.
Does the P-ready signal, you said like if there wasn't a following command, we could just extend all of this off the screen. Does that include the P-ready signal? Or does the P-ready signal just go through this? Or does that depend on device?
Let's see, the P-ready. So the screen raised, so P-ready should drop on the next, whenever the peripheral is done.
Okay.
So it has to drop.
So if this was just the one command we were running, we would see these changes, and then everything would carry off into the distance except for P-ready, which would still drop.
Yeah, and then, so then you could say this thing drops, the bus tries to get ready for the next cycle, okay, it's instantiating data, and then it drops in. So here we already see that you need at least, for this bus architecture, you need at least one cycle to instantiate data, and another cycle to lock it in, and then you're instantiating data, lock it in, so at least your throughput's half of the clock speed. Well, we'll try and do this one. All right. Well, no, I'm gonna do this one. You guys aren't gonna do this one. I'll do this one. Is that right? Yeah. Okay. So let's say we're trying to control an LED. And so now I want to talk about like what's inside this device. What's one way to instantiate what's inside those peripherals so that it responds correctly to the inputs from the bus. So here we just talked about what the bus data was. Here's the bus data coming in to the peripheral, and now we have to do something. So control an LED with the lowest significant bit of this register. So I have a 32-bit register here, and so we would need some way to tell the peripheral, pay attention. So we can say, when you're writing, when it's enabled, and when deselect occurs, I want to enable the D flip-flop. That's when it should be doing something, right? So we use AND gates a lot here, it's just to mask. All these things have to be true for something to happen, okay? We're gonna take, the data is gonna go into the 32-bit register, so we're gonna take all 32-bit lines in here. We could have just gotten away with one D flip-flop if we were just the lowest bit, but here we already saw there was a 32-bit register, so we're gonna take all 32-bit lines. We use some slash with 32 to denote that that bus has 32 lines in it, okay? And then we're gonna take the output of this into LED. Now, I'm not gonna take 32 lines in parallel into that. In fact, I used a single wire there to denote that. And so just to make explicitly clear, I'm showing you to take the 0th element of that bus, break it off, and put it into that LED. There should probably be a resistor there. We'll ignore that fact for now. All right, we got P clock. P clock is gonna go to this thing. So it's only gonna be clocking in data when it's enabled. It's always ready, right? It's whenever that clock comes in and everything is variable, it's ready immediately. So one way to say that is just we're gonna tie this to VDD. So this is a symbol that means logical 1. Oh, that's it. We'll stop there. Any questions in the last 2 minutes about this?
So the enable input to the register, that's saying that it will overwrite whatever is in there with what's like the data.
Yeah. So it means for disabled, it ignores the clock input and holds the state. If it's enabled on the next rising edge of the clock, it will take whatever's in D and store it in and make it represented on Q.
And if you're reading, how does that?
That's the next example. You gotta wait till Wednesday. I can't tell you now. Last question? Well, and write your name on them, on your friends, if you didn't have one, or if you didn't have one, just come and tell me.
I promise I have both pencils somewhere.
It's so big. It's really big, but like it's heavy, but it's really nice. I could take stylus now.
Maybe 270.